I welcome you all on this lecture on dynamic response of the first order system. So, till now we have seen the basic building blocks for various types of systems, say mechanical system, electrical system, hydraulic, pneumatic, thermal, and then we have seen the combinations of the system also, such as electromechanical system, hydromechanical system and so on. Now, in this lecture we will be seeing the dynamic response of the first order system or dynamic response for the systems whose dynamic behavior can be described with the help of first order system. So, we will see that how these systems behave or how we can find out the behavior of the system. So, as I was telling you, I have been talking to you throughout this lecture. The most important function of the model is to predict what the output will be for a given particular input. In fact, that is the most important function or most important job of any dynamic system or job of any modeling exercise, that is we want to know the output of the system for a given particular type of input. Now, we are concerned about these three aspects mainly, that is the first one is what happens at static condition or say that is when steady state is reached, what happens, what is the behavior, what is the magnitude, okay, and how the output changes with time when there is change in input. Okay, so, if input is changing, how output changes with time and how output changes with time when there is change in input with time. Okay. So, these are the three cases which are particularly important in simulation study of the system. Now, as we have seen for various system, output and input both can be function of time, and the differential equations describe the relation between the input and output. These differential equations includes derivative with respect to time, thus their solution indicates how response will vary with time. Now, as all of you know, dx by dt represents the first order system and it describe the rate at which x varies with time. Similarly, d square x by dt square represents a second order system and it describes how dx by dt varies with time, and similarly we describe dnx by dt n for the nth order system. So, here in this lecture we will be discussing about a system involving dx by dt term, which we call it as the first order system. Now, the first order system examples are many in fact. So, let us take this example that is the water coming out from a tank, okay, and suppose first we consider the natural response. Natural response means that here there is no input, okay, so there is no tap filling this tank, okay. So, in that case let us see how this H varies, okay. So, for the natural response, okay, as I said, consider the water flowing out of a tank, and for this system the hydraulic resistance R can be written as P1 minus P2 is equal to RQ. Basically the equation very similar to that of the electrical resistance, that is V is equal to I into R, okay, where here Q corresponds to I and V P1 minus P2 corresponds to V, and of course R represents here the hydraulic resistance. Now in this case we know P1 minus P2 as rho GH, and the Q will be basically dV by dt, and I am using a minus sign just to indicate that this rate of flow is negative, that is it is decreasing, okay. So when I put it here, then what I get, rho GH is equal to RA minus DH by dt, and this is how it looks like. Now we call this equation is a first order differential equation, because here you can see that our H is the output variable, that is our aim is to find out how H varies with the time, and this is natural response because here there is no forcing function, okay, nothing, we have assumed that there is no other tap which is going to fill up the water, okay. So this is 0. So this equation is first order differential equation, and as I said here there is no input to the system forcing the variable to change, and thus the response of the system is called the natural response of the system. Then we could have a condition where there is a tap with certain water coming in into the tank, okay, and then the response of the system whatever will be there, that we call it as the force response, fine. And in this case there is a flow of water in the tank, and we have already seen this derivation when we were discussing with the hydraulic system. I just want to take you to the first order differential equation in case of force response, okay, that is in case the flow of water is taking place into the tank, okay, then how the system behaves. So for defining the hydraulic capacitance, I can write Q1 minus Q2 is equal to C dP by dt here, and then here for the valve I can write P1 minus P2 is equal to RQ2, and this is basically my rho GH. So RQ2, so I find out Q2, I substitute this Q2 value here, so this is what I get, Q1 minus rho GH by R is equal to C dP by dt. Next I can substitute the value of C, which is A by rho G, rest of the things remain same, okay, and this is how this is what is the reduced equation, and this is how I can write the equation. Now here you see what we have the output variable H here, and there is a first derivative of the H here, okay, and we have the input variable Q1 here, and this is basically the forcing function, okay. So the response of the system or say response of this differential equation, the first order differential equation, is what we call the response in presence of the forcing function, okay. I hope the concept is clear. Then let us see the total response of the system. Now if I talk about the total response of the system, it could be basically divided into divided as the summation of the two response, okay, and these summation are, first one is the transient response and the steady state response. Now transient response is basically it occurs when there is change in input to the system, okay, and as the name indicates, the transient response died out after some time, okay, and the steady state response is the response which remains after transient have died. And when we sum up both these type of response, what we call it as the total response of a control system, or it is total response of the element of a system. Let us take an example. Suppose I have got a spring here, and say there is some hanger here where I can add up a weight, okay, and say the displacement of a spring takes place in this direction. Now what happens, initially there is no weight on the hanger which is attached to the spring, and after some time I add a weight to it. So what I am doing, I am changing the input. Initially the input is 0 and then the input is that of equal to the weight. And now as all of us practically feel that or what practically we have observed that after adding the weight, what will happen, the spring will oscillate a little and then it will settle at a permanent displacement at a displacement, specific displacement of the spring, and that specific displacement value will depend on how much weight has been added and what is the stiffness of the spring. Okay. So, here if we look at the response of the system, this is what happens. You can see that initially there is variation in the displacement, okay, and then this displacement settles for a particular value. So, this zone where there is a variation in displacement, what we call it as the transients, or this portion of response is what is called as the transient response, and this portion of response what we call it as the steady state value. Okay. And of course, this value of the displacement, as I said, is the displacement due to the added weight, and of course, this depends on what is the weight and what is the stiffness of the spring. So, you can observe here the response of the system to be consisting of the transient response and the steady state response. Okay. Now, the previous example which I have seen, that is adding of the weight on the hanger, what it is basically, it is a input to the system, okay, it is a input to the system, alright, and that type of input what we call it as the step input, that is initially the value is 0 and then a definite value is given. So, this type of input is what we call it as the step input. Okay. We need to know the various types of inputs for which the system is subjected to in order to know the behavior of the system. Okay. Then there could be another type of input what we call it as the impulse input, okay, and it is basically impulse at some time. Here at certain time value, some time value, you can have some value of the input, and that type of input what we call it as the impulse input. Then we can have another type of input, a ramp input. Ramp input means the input which varies with time, okay, linearly basically. Here if you say that the input is y, then y is equal to kt, okay. This type of input is what is called a ramp input. Other type of input could be the sinusoidal input, and you can see here the curve for variation of input with time is sinusoidal in nature, and here this input could be written as a k sin omega t, where k is a constant and omega is the angular frequency which we write as 2 pi f, and where f is called as the frequency. So, your system could be subjected to any of these 4 types of inputs, that is step, impulse, ramp or sinusoidal. Yeah. Now, let us see the first order system. Okay. So, in a block diagram mode, this is how we represent our system, and say this system is subjected to certain input y t and we get a output say x t. Now I can write the expression for this first order system something like this. Okay. As we have seen that in case of water tank, okay, the expression is something very similar to like this, that is we have a constant, then dx by dt, that is the derivative, first derivative of the output plus some constant into the output is equal to some constant into the input. Okay. And here you can see that the highest order for here derivative is 1 here. So, this is what we call as the first order system. Now, as we have seen, there could be two types of responses for this system. One is the natural response and another is the forced response. So, let us see the natural response of this system. Now, if natural response we are talking about, naturally then the input has to be made 0, as in the case of the water tank example which we have taken previously, there was no flow from the tap. Okay. So, let us take here this input is 0. Now, when this input is 0, this is the system equation, fine. Now, let us suppose the solution for this expression is x is equal to a into e to the power st, where a and s are constant. Then what we can do, we can determine the value of this constant, say s here, by substituting this solution into this equation. Now, if I substitute this solution into this equation, this is what I am going to get: a1 a s e to the power st plus a0 a e to the power st is equal to 0, and from here I can find out the value of s as minus a0 by a1. Okay. Now, so my expression becomes x is equal to a into e to the power st. Okay. And when I substitute the value for s, this is minus a0 by a1 into t, this minus a0 by a1. So, this solution becomes like this. Now, I can determine this constant a from the initial condition. Okay. So, a can be found by initial condition, say at time t is equal to 0, x is equal to 1 here. So, when I substitute t is equal to 0 here, x is equal to 1, I get a is equal to 1. So, the output can be given as this one, x is equal to e to the power minus a0 by a1 into t. Okay. And at t is equal to 0, x value is 1, and then rest of the behavior we can see here, that is this is exponentially decaying behavior. So, this is what is going to be the natural response of the first order system. Okay. Now, let us see the response of the first order system with a forcing function. Okay. For example, that water tank example which we have taken, say there is a tap from which the water is coming into the tank, alright. So, if that is the equation, say a1 dx by dt plus a0 x is equal to b0 y, let the solution, now here you see that this part is not 0. Here this b0 y basically represents the forcing function. So, let the solution in this case be x is equal to u plus v, and say u is the transient part and say v is the steady state part. Okay. Now, let us substitute this x is equal to u plus v here. Okay. So, when we put it here x in place of x u plus v, this is what we get, and then I club the terms related with u here and the terms related with v here, and here is my forcing function. Now, suppose this part, okay, I take it as 0, that is if I make this part as 0, then naturally this part is going to be equal to b0 y, alright. Then the first equation is the differential equation with natural response, whereas the second is with the forcing function. Here you can see the second equation is a first order differential equation with a forcing function, and the first equation is a first order differential equation with the natural response here. Okay. So, for the natural response we know the solution, u is equal to a constant a, which we can determine from the initial condition into e to the power minus a0 by a1 into t. Okay. Fine. Now, for the force response output will depend on input, that we know. So, let input be a step function. Okay. For the force response, output has to depend on the input. For natural response, there is no input, so that value is 0, input value is 0. Okay. Now, suppose here let us take a step input in this case, okay, that is at t is equal to 0, say the step size of the step being k. Okay. So, say my input is something like this, that is initially it is 0 and then it has got a step size of k, this is time, okay, and this is my say input. Now, so what happens, this was my equation for the force response part of the total differential equation, okay. Fine. Now, let us assume the solution to be V is equal to B, a constant. Okay. Then what I do, I substitute this solution into this equation, this term will be becoming 0 and here what I will have a0 b is equal to b0 and input I have assumed the k value. Okay. The input is k here, this value which I have taken. So, I substitute it here and I find out the value of the constant this b, that is b0 by a0 into k. So, the solution this v is going to be b0 by a0 into k, and so the complete solution x will be u0 u plus v, that is the natural response part plus the force response part. Okay. And when I substitute for u and v, this is what equation I get. So, this is your natural response part and this is your force response part. Okay. So, I put that equation here. Now, here you can see that there is a constant a, alright. I can find out this constant again using the initial condition, say at t is equal to 0, x is equal to 0. Then if I put that, I get the this is 0, this term will be 0. So, I have 1 a, so a will be minus b0 by a0 into k, and then I can substitute this a into this expression, this is what I get. Okay. So, this part is basically the natural response part and this part is the force response part. Okay. So, this is my general expression, general solution rather. Okay. Now, if you look at this equation, you can see that at t tends to infinity, this part is going to be 0. Okay. So, this part when becoming 0, whatever I am getting, it is a constant term b0 by a0 into k, and this term is what we call it as a steady state term or steady state response. So, steady state response x is b0 by a0 into k. Okay. So, for this input, step input of size k, okay, the response, that is output, is this one, and this steady state value which occurs at t tending to infinity will be b0 by a0 into k. Okay. So, this is the input and this is the resulting output of the first order system. Okay. So, fine. I have taken one example of the first order system, that is that of the water tank, okay, filling of a tank. Fine. We can have another example, that is a DC motor. Now, we have discussed this DC motor modeling in the electromagnetic section, okay, modeling of electromagnetic systems. Okay. So, here relation for an armature control motor, this is what we had, that is VA is the armature voltage, omega was the angular velocity of the motor, LA is the inductance of the motor, IA is the current, and RA is the armature resistance of the motor. Okay. So, and the second equation for the system was this was that is acceleration of the load I d omega by dt, this was K for Ia minus Rb omega, where Rb is that damping, okay, or the bearing resistance. Now, here what we can do is that we can neglect say inductance part, alright, and we can substitute Ia in the second equation, okay, from the first one to get the relation between input VA and the output omega. And if you do that, I am not explaining you, you can work it out. If you do that, this is the equation which you are going to get. Okay. So, here you see you have input part VA and here you have output part omega. So, this equation is basically the first order differential equation, okay, and we can compare this first order differential equation with the general form of the equation which we have seen. Okay. You can see that here x corresponds to the output here. So, here is omega, here x, so omega, here input this term corresponds to y here, and so of course A1 is a constant here, A0 is 1 and B0 is 1 by K3, like that. Okay. So, this way we can have one to one relationship, okay, and then we can see the response for this system similarly as we have seen for the general case. Okay. So, I leave it as an exercise to you, just have a look at it. Now, let us see the time constant. Okay. So, our general expression, general solution for the first order system has been this one, okay, and we know that this B0 by A0 into K was the steady state value. So, it is steady state value into 1 minus e to the power minus A1 by A0 by A1 into T. Now, here if you look at this equation, if I put T is equal to A1 by A0, then here those A0, A0, A1, A1 terms will get cancelled, okay, and what you will be getting is that 0.63 evaluation of all these things. Okay. So, what we can say that at T is equal to A1 by A0, the x value is 0.63 times that of the steady state value, okay, and this time tau of magnitude A1 by A0 is what is called the time constant of the system. Okay. And so, the response for first order system for a step input we can write in terms of the time constant as x is equal to steady state value into 1 minus e to the power minus t upon time constant or minus 1 by time constant into t. So, if we look at that expression, then as I said, at one time constant the fraction of steady state output is going to be 0.63. Okay. Likewise, we can look at for 2 time constant, 3 time constant, and at infinity the value is going to be that of 1, that is which is that steady state value. Okay. And this is how we can plot that, okay, that is here at 0.63 and 0.86, 0.95 and at 1. So, you can see that at 1 we get the steady state value. Okay. So, these are the references. If you want to read further about this, the Bolton and our book has got some discussion on this. Okay. So, I thank you, and in next lecture we will be seeing the behavior of the second order system. Thank you.